Now I am going to start module 2 of chapter 5. This module is devoted to the study of one-dimensional parabolic equation. The example of parabolic partial differential equation which occurs most frequently in nature or any physical system is the heat equation or the diffusion equation. Thus, we have considered heat equation for the entire discussion in this module. We have taken one-dimensional heat equation because one-dimensional equation is easy to solve and the idea can be extended to solve the problem in 2 dimension and 3 dimension. Apart from that, there is some physical situation where heat flows only in one direction. Therefore, it is worthy to study the one-dimensional heat equation. In this module, we shall first derive the fundamental solution of one-dimensional heat equation. Then we shall use the separation of variable method to find solution of one-dimensional equation. Now we are going to start the first slide of this module. We are considering one-dimensional wave equation which is written in 1 del t equals to kappa del 2t del x square, where x varies from minus infinity to plus infinity and t is time greater than 0. It can be verified that capital T x t is equal to 1 divided by square root 2 pi kappa t exponential of minus x minus xi square divided by 4 kappa t is a solution of equation 1. If we compute del t and del 2 to del x square from the expression 2 and put in equation 1, it will satisfy equation 1, and the solution which is written in equation 2 is called the fundamental or elementary solution of the parabolic equation 1. If you see the solution, you can observe that txt is an analytic function of x and t for all t greater than 0 and it is positive for all x. Thus, the entire x axis is the region of influence for this parabolic equation. Also, it is to be noted that this solution tends to 0 or the value of t tends to 0 as mod x tends to infinity. So, these are the properties of the fundamental solution of equation 1. Now, we want to find solution of equation 1 together with the initial condition t x 0 equals to f x. For that purpose, we are using separation of variables technique. So, we put capital T is equals to capital X into capital tau. So, if we substitute this expression of capital T in equation 1, we obtain the equation which is written in 3. 1 by capital X d2x dx square is equal to 1 by kappa tau d tau dt. So, thus we separate the variables or the functions capital X and tau in this way. Let the separation constant is lambda. Now, equating 1 by kappa tau d tau dt equals to lambda, we can solve or we can find the value of tau as c into e to the power kappa lambda t. If lambda greater than 0, capital T grows exponentially with time, and this is unrealistic from the physical point of view. We assume that f x tends to 0 at mod x tend to infinity and the value of capital T is bounded. That means mod t is less than m as mod x tends to infinity. So, txt to remain bounded, we have to take lambda negative. So, for that reason we have chosen lambda as minus mu square, where mu is a real constant. Thus, putting lambda is equal to minus mu square, the expression for tau becomes tau equals to c e to the power minus kappa mu square t. Now, there is another equation in capital X which is written here, d2x dx square plus mu square x equals to 0, and whose solution is capital X equals to c1 cos mu x plus c2 sin mu x, where c1 c2 are constants. So, the general solution of capital T becomes t equals to a cos mu x plus b sin mu x into e to the power minus kappa mu square t, where we modified the constants as capital A is equal to c c1 and capital B is equal to c c2. Since fx is in general non-periodic, we consider Fourier integral instead of Fourier series. So, instead of summation, we are considering integration. Also, a and b are arbitrary. We consider them as function of mu. Now, we have to consider all possible values of mu. Thus, the principle of superposition gives the summation of all product solution capital T equals to integration of 0 to infinity capital T x t mu d mu. Now, substituting the value of capital T from equation 4, we get capital T at x t equals to integration 0 to infinity a mu cos mu x plus b mu sin mu x into e to the power minus kappa mu square t d mu. We have the initial condition t x 0 equals to f x. So, f x equals to 0 to infinity a mu cos mu x plus b mu sin mu x, and here we put t is equal to 0. So, e to the power 0, that becomes 1. Thus, we obtain the equation 7. If we see the equation 7, this is we can use the Fourier integral theorem. The Fourier integral theorem says that if u is equal to 1 by pi integration 0 to infinity integration minus infinity to plus infinity f x cos mu u minus x dx d mu. So, now replacing u by x and x by y from the previous expression, we get the value of the integral as f x equals to 1 by pi 0 to infinity minus infinity to plus infinity f y cos mu x minus y dy d mu. Now, we expand this cosine function as cos mu x minus mu y is cos a cos b plus sin a sin b. Now, we separate the integral into two different as sum of these two terms as 1 by pi integration 0 to infinity cos mu x minus infinity to plus infinity f y cos mu y dy plus sin mu x integration minus infinity to plus infinity f y sin mu y dy d mu. That is so, in this expression can be written in this form also 0 to infinity a mu cos mu x plus b mu sin mu x d mu, where A mu equals to, if you see the previous expression, so A mu is equal to the expression which is in this integral, that means A mu is equal to 1 by pi integration minus infinity to plus infinity fy cos mu y dy, and B mu is 1 by pi minus infinity to plus infinity fy sin mu y dy. Now, if we substitute 10 in 7, we get fx equals to 1 by pi 0 to infinity minus infinity to plus infinity fy cos mu x minus y dy d mu. So, the expression for capital T or the general solution of capital T is T is equal to 1 by pi 0 to infinity minus infinity to plus infinity fy cos mu x minus y e to the power minus kappa mu square t dy d mu. Now, this equals to 1 by pi 0 to infinity fy minus infinity to plus infinity e to the power minus kappa mu square t cos mu x minus y d mu dy. Now, capital T is equal to 1 by pi integration 0 to infinity integration minus infinity to plus infinity fy cos mu x minus y e to the power minus kappa mu square t dy d mu. Now, in this step we are interchanging the order of integration. So, it becomes equals to 1 by pi integration minus infinity to plus infinity fy integration 0 to infinity e to the power minus kappa mu square t cos mu x minus y d mu dy. Now, we want to compute the integral which is written in this square bracket. In the last section, we have discussed about fundamental solution of a one dimensional heat equation. Now, I am going to discuss or to find the solution of heat equation using the separation of variables method. The separation of variable methods is a very powerful method. It can be applied in a wide variety of partial differential equation. Using this technique, I shall solve one dimensional heat equation in Cartesian coordinates, plane polar coordinates and spherical polar coordinates. So, for that discussion, we have to go to the slide show. We know the relation 0 to infinity e to the power minus z square cos 2bz dz equals to root pi by 2 e to the power minus b square. We can obtain this relation or the value of the expression which is written in the left hand side using the property of gamma function where b is real. Now, in this relation, if we substitute z as mu into square root kappa t and b is equal to x minus y by 2 into square root kappa t, it becomes 0 to infinity e to the power minus mu square kappa t cos mu x minus y d mu is equals to the expression which is written here. So, if you substitute the value of this integral in the expression 11, we obtain capital T is equals to 1 by 2 square root pi kappa t integration minus infinity to plus infinity fy e to the power minus x minus y whole square divided by 4 kappa t dy. Thus, if fy is bounded for all real values of y, then 12 gives our required solution. Now, we shall take one example. In this example, this is a one dimensional infinite solid and the surface A less than x less than b is initially at temperature T0 and at 0 temperature outside the surface. We have to show the expression for capital T which is written here, where ERF is the error function. So, the problem can be written as we have to find the function capital T which satisfies the one dimensional heat equation, which is written here, subject to the initial condition T x 0 equals to C 0 for A less than x less than T, where T 0 is some constant and T x 0 equals to 0 outside this region. Now, if we look the general solution or the fundamental solution, the expression for capital T can be written in this way. Now, the range of y is minus infinity to plus infinity, but for this problem the temperature is 0, here capital Fy is T0 and capital Fy is equal to 0 outside the region A and B. So, we can put the value of Fy as T0 within the range A to B, and outside this region Fy becomes 0. So, the integral can be written like this. Now, we substitute this minus of x minus y by 2 square root kappa T is equal to xi. So, we are transforming the variable from y to xi. So, in terms of the variable xi, the integral becomes this, which is written here, and the corresponding the limits also change. Now, this integral can be written in this way, we can break the integral in this way. So, this is T0 by 2 by square root pi 0 to b minus x by 2 square root kappa T to the power minus xi square d xi minus 2 by square root 0 to a minus x by 2 square root kappa T to the power minus xi square d xi, and this function is known as error function. So, the first integral can be written as error function of b minus x by 2 square root kappa T minus error function at a minus x by 2 square root kappa T. Thus, we get the required solution for capital T for this particular problem. The one dimensional heat equation in Cartesian coordinates can be written in this form, which is given in equation number 13. Here we are again using the method of separation of variables. So, T is assumed as product of capital X and tau, where capital X and tau are functions of x and t respectively. So, substituting the expression for capital T in equation 13, we obtain the equation 1 by x d2x dx square equals to 1 by kappa tau d tau dt. So, in this way we are separating the variable x and t. Let lambda be the separation constant. So, the equation for capital X and tau becomes d2x dx square minus lambda x equals to 0 and d tau dt minus kappa lambda tau equals to 0. The solution for, first of all we assume that the separation constant lambda is a positive number. So, lambda is greater than 0. So, lambda can be written as lambda equals to mu square, where mu is a real constant. So, putting this value of lambda, the equation for capital X becomes d2x dx square minus mu square x equals to 0. So, the solution can be written as x equals to C1 e to the power mu x plus C2 e to the power minus mu x, and the solution for tau can be obtained easily as tau t equals to C3 e to the power kappa mu square t, where C1, C2, C3 are integrating constants. So, substituting the values of capital X and tau in the original equation, we get the expression for capital T as A e to the power mu x plus B e to the power minus mu x into e to the power kappa mu square t, where capital A is equal to C1 C3 and capital B equals to C2 C3. Now, I am going to the second case where lambda equals to 0. So, if lambda equals to 0, the solution for capital X becomes C1x plus C2 and the solution for tau becomes tau equals to constant, which is equals to C3. Therefore, the required solution becomes capital T equals to Ax plus B, where A is defined as C1 C3 and B is equal to C2 C3. Now, the last case when lambda is less than 0. So, lambda can be written as minus mu square, where mu is a real constant. So, capital X becomes C1 cos mu x plus C2 sin mu x and the tau is equal to C3 e to the power minus kappa mu square t. So, the solution for this case can be written as T is equal to, which is given in this slide. Here we also modified the constant C1, C2, C3 in this way. Capital A is C1, C3 and capital B is C2, C3. Now, this is the example where we need to solve the heat equation in Cartesian coordinate system. So, in this problem there is a uniform rod of length L whose surface is thermally insulated and initially it is in temperature T is equal to T0. At time T is equal to 0, one end is suddenly cooled to T is equal to 0 and subsequently maintained at this temperature. The other end remains thermally insulated and we have to find the expression for capital T. So, this is a one dimensional problem. So, we have to find solution of one dimensional heat equation, which is written here, subject to the initial condition capital T x0 equals to T0, where x is 0 lies between 0 and capital L. Capital L is the length of the rod and the boundary condition is T at the end x equals to 0, it is 0 and the other end this is insulated. So, the normal derivative of the temperature del T del x is 0 for T greater than 0. If we call back the solution of a Cartesian one dimensional heat equation in Cartesian coordinates, this is the general solution. Capital T is equal to A cos mu x plus B sin mu x e to the power minus kappa mu square t. Now, we need to satisfy the boundary condition and the initial condition for this problem. So, if we satisfy the boundary condition T 0 t equals to 0, so it gives capital A is 0 and the boundary condition del T del x L t equals to 0, it gives cos mu L equals to 0 and we know the solution of cos mu L equals to 0 gives mu L equals to 2n plus 1 into pi by 2. So, this gives the value of mu as mu equals to 2n plus 1 into pi by 2l, where n is an integer. Thus, substituting the value of mu in the general expression, we get capital T is equal to B exponential of minus kappa 2n plus 1 by 12 square into pi square t into sine of 2n plus 1 by 12 pi x. Using the principle of superposition, the linear combinations of all solution is also the solution of the original equation. Thus, we obtain the expression for capital T as sum over n Bn into exponential of this sine of this, which is written here. Finally, we have to use the initial condition T x0 equals to T0. So, using that initial condition, we obtain T0 equals to sum over n Bn sine 2n plus 1 by 12 into pi x. So, this is a very well known series, and this is called the half range Fourier sine series. And we know how to find the constant Bn from this half range Fourier series. So, to obtain Bn, we need to multiply this expression with sine 2n plus 1 by 12 into pi x, and then we need to integrate over 0 to L. That will give the value of Bn as 4 T0 by 2n plus 1 into pi. So, putting this value of Bn in the solution, we obtain the required temperature distribution as capital T equals to, which is written here. Now, I am going to discuss about the solution of heat equation in plane polar coordinates. In plane polar coordinates, the heat equation takes the form. So, there are two independent variables, which one is time t and another one is the radius vector small r. So, now we are going to apply the same process, the method of separation of variables. For that, we are writing capital T as product of capital R and tau, and substituting this expression in the equation 18, we obtain the equation which is written here, 1 by r d2r dr square plus 1 by r dr dr equals to 1 by kappa tau d tau dt. So, in this line we separated the variable r and t, and now we are assuming the separation constant as mu square. So, this equals to mu square gives two ordinary differential equation, one is in capital R, other one is in tau. So, the equation in capital R is d2r dr square plus 1 by r dr dr plus mu square r equals to 0, and the equation for tau is written here. The solution of the tau equation is very easy to find, and the solution tau is equal to C3 to the power minus kappa mu square t. Now, if we look the equation for capital R, this is again a Bessel differential equation of order 0. So, its solution is the linear combination of two Bessel's functions of first and second kind. So, capital R can be written as C1 J0 plus C2 Y0. Thus, the required solution of the equation is capital T is equal to A J0 plus B Y0 into e to the power minus kappa mu square t, where capital A is equal to C1 C3 and capital B is equals to C2 C3. In this section, we shall discuss about the solution of one dimensional heat equation in spherical polar coordinates. The heat equation in spherical polar coordinates can be written. We are again using the method of separation of variables to find solution. So, we substitute capital T as capital R into tau. So, substituting that, we get an equation which is written here. Let mu square is the separation constant. So, equating mu square is equal to the R equation and tau equation, the equation becomes d2r dr square plus 2 by r dr dr plus mu square r equals to 0, and the tau equation becomes d tau dt equals to minus kappa mu square tau. It is easy to find solution of the tau equation. This is the exponential function. So, the solution can be written as tau equals to C1 e to the power minus kappa mu square t. Now, to solve the r equation, we need to substitute capital A's variable as smaller into capital R. Now, the r equation becomes to the equation in terms of the variable capital S as d2s dr square plus mu square s equals to 0, and its solution is s equals to a1 cos mu r plus b1 sin mu r. So, capital R becomes a1 cos mu r plus b1 sin mu r by small r. Hence, the solution of the equation 20 becomes t equals to e to the power minus kappa mu square t by r cos a cos mu r plus b sin mu r, where capital A is a1 c1 and capital B equals to b1 c1. So, this is the general solution of heat equation in spherical polar coordinate system. Therefore, in module 2 of chapter 5, we have discussed about the solution of one dimensional heat equation. Firstly, we have discussed about the fundamental solution of the heat equation. Then, using the technique of separation of variables, we find solution in 3 different coordinate systems. In Cartesian coordinate system, the solution is the Fourier modes, and in plane polar system, the solution is the Bessel function, and in spherical polar system, we obtain the solution in terms of the Fourier modes. Thus, we end module 2 of chapter 5.